Hello, good evening, all.
Good evening.
Yes, so we'll start today's session.
Good evening.
Yes, I am recording the session and will later upload the YouTube link for that. Okay, so just a quick check. How many of you have watched week 5? No one has watched. Not even a single lecture you guys have watched. Even the first part.
Yeah, I have gone through only first lecture only.
Okay, first lecture you have been through. Okay,
Yes, that portions. Yeah.
all right. What about others?
Not first yet.
No, ma'am.
No,
No.
ma'am.
So, are you guys doing week 4, like, or maybe week 1 to 4 because next week is exam?
Yes, ma'am. Yes, ma'am.
Yes,
Yes.
Yes,
ma'am.
ma'am.
Okay, but week 5 credit assignment submission is Wednesday. So, at least watch the lecture and try to submit the assignments. Yeah.
Okay, ma'am.
Yes. So, we'll start the session for week 5. I'll just go through whatever is there in week 5 currently. Okay. Are you all able to see my screen?
Yes.
Okay.
Yes,
Yeah.
ma'am.
You are able to see this, right?
Yes, ma'am.
Chapter 5.
Yes.
Okay. Yes. Okay. So in chapter 5,
Madam, this PDF is available for us or no?
no, we'll upload mostly
Okay.
by
Yeah.
tomorrow.
Thank you.
Yeah. Okay. So, okay. First of all, what all we are looking at in week 5. Okay. So the first thing we have started with. So in week 4, we stopped at common distributions, right? And we look at in week 4 we had looked at all the CDF, PDF, and those common distributions, correct? These all for a random variable. Now in week 5 we are going to start with function of random variable. We are going to start with function of a random variable. Function of random variable, what is its PDF, what is its CDF. Okay, then we are going to look at expected value. So we had seen in week 3 the expected value for discrete distribution, but here we look for expected value for a continuous distribution. All right, and then we are going to look at joint distribution. Joint distributions where one is discrete, where one random variable is discrete, and the other random variable is continuous. In week 1 and 2, we have looked at the joint PMF when both of the random variable were discrete. But here we are going to look at what happens, how do you define the joint distribution when one of your random variable is discrete and the other is continuous. So these are the topics that we are going to cover in week 5. Okay. Let's start with function of random variable. So why do we really need a function of random variable? We already have a random variable x, right? And now, so what we are saying is, since we already have a random variable, and if we know their distribution, what is their PDF and all that, we can have such cases where you can define another random variable in such a way that that another random variable is just a function of this random variable. So you can have a situation where the another random variable is just defined as, let's say, g of x. Okay, for example, just in case of look at the first example here. It says, suppose we model the length of a square as a random variable x. Okay, we have a square and we have modeled the length of the square as a random variable x. Let's say x denote the length of the square. Okay, and it is some random variable. But what happens if we want to model the area of the square, right? So you know that for square the area is just you will say length square, right? So you can do just x square, and x square is nothing but just a function of the random variable x. So if you know the random variable x, its PDF, CDF, you can easily find the distribution for the function of random variable. So you don't have to go and define it in some other different random variable. If you define it in such a way, then it's easy to like you can find the PDF, CDF for these random variable easily. Then the other example that was given is, let's say uh, you have some fluid for which the density is constant, right? So, and if you model the volume of the fluid by the random variable x, then the weight can be modeled as rho times x. So you know density is equal to weight by volume, right? So you can model just few cases where the function of random variable has arises, and uh, in many, it just two examples, but you can have many such examples that you see in real life, where if you can model, if you know what is the distribution for a random variable x, and you have to model the distribution of its function. So such cases will arise many times, and it's good to know how to find the distribution in such cases. Okay. Now you have a very simple example here. So the example says, let x is uniform in 0 1. Okay. So you have a random variable x, okay, and you say it is uniform in 0 1. So uniform in 0 1 means you have, so what is the density? What is the PDF for this? If x is uniform in 0 1, can somebody tell what's its PDF?
One.
PDF is
PDF
1.
will be for x.
Sorry, PDF will be,
If x is less than 0, then it is 0. For z between
no, so you can directly
and
say
after 1, it is 0.
fx of x is just 1 for x lying between 0 to 1, and
0 to 1,
otherwise 0.
0.
This we can say.
Yes.
So okay, you know that x is uniform 0 1. Now we are defining another random variable y. Okay, we are defining another random variable y. Mm. So what is y? Y is just 2x. So we have to find what is the distribution of y. So if x lies between 0 to 1, and we are saying y equal 2x, so what should be the range of y?
0 to 2.
0 to 2.
0 to 2, right? Now, how will you find the distribution of y? So, saying the distribution of y, we are interested in finding it CDF. I mean, you not CDF. You want to know what is the distribution of y going to be. Okay. So basically, what you will do is now you know y lies between 0 to 2. So let's try it here only.
Ma'am,
Yeah.
ma'am,
Hmm.
yeah, so in the, like discrete random variables,
Hmm.
if I have a random variable x and I have its function like x square or something, so
Hmm.
the value of the random variable changes, but it's a PM is calculated using that only, na, in the same way. The old
I
PMF.
didn't
That's
get your
what we are
question.
trying to do here, right?
So
I'm saying we are trying to
you're
find the
saying
new
if
PDF
x is
using
a if
old PDF,
huh, yes, we
like
are
we did
trying to
for
find the
discrete random
new
variable.
PDF. Yes, yes, yes. Huh.
Okay,
We are
okay,
trying to do
okay.
the same thing. Yeah. So now, how will you find the distribution of y? So you know y lies between 0 to 2. Okay. So you have y that lies between 0 to 2. Let's draw it here. So let's draw y equal to x here. So you will have something like this. Okay. Okay, let's be more something like this. Okay. So this is y equal to x. Now, uh, okay. So when x lies between, okay, leave that. So fy of y. So what do you mean by fy of y? It is just probability
CDF of Y.
y less than equal to y,
Yes,
right?
ma'am.
But what is capital Y? What
2x.
is capital Y? This is 2x. So
2x.
2x is less than equal to y, right? And this can
Yes,
be
ma'am.
written as probability that x is less than equal to y by 2,
Y by 2.
right?
Yes, ma'am.
And you can write this as CDF of x at the point x equal small y by 2, correct?
Yes, ma'am.
Now this is so what you did is you wrote the CDF of y in terms of the CDF of x. This is what you got.
Yes, ma'am.
Okay. All right. So how will you write this CDF? You know that if you have a random variable x that is uniform in A to B, then the CDF of x is given by x minus a upon b
B
minus a.
minus A.
This you have seen in week 4.
For
Okay.
X between A and B.
For
For
x,
X between
yeah,
A
for
and
x
B.
between a and b. Okay. Now, all right. So now in place of x, you just have y by
Y by
2,
2.
right?
By 2.
So
Yes, ma'am.
what is fx of y by 2? It is going to be y by 2
Minus
minus
0.
minus 0 because x is bit uniform in 0 to 1,
A is
0
0.
to 1. A is
right?
0, B is 1.
Yeah. Okay. Divided by b minus a, that is just 1.
1
1
minus A.
minus 0. Yes.
So you just got fy of y to be
Y
y
by
by
2.
Y
2,
by 2.
right? So this is what you got. So CDF of y is just y by 2 for y lying between 0 to 2. And to find the PDF, you can just differentiate your CDF. So if you differentiate the CDF, you will get 1 by 2. So what exactly you got is that your y is also uniform in 0 to 2, right? This is clear.
Could
Yes,
you
ma'am.
repeat
Yes,
the
yes, ma'am.
last part about
Last part is
differentiating?
same. Yeah. So you found fy, like this is what? This is your CDF. Fy of y is this y by 2. Okay. And if you have to find the PDF, fy of y, what you will do? You will differentiate capital Fy of y with respect to dy. And what is Fy of y? You have y by 2. So you will differentiate y by 2 with respect to y, right? And what is this differentiation? It is just 1 by 2. So you got, what you got is, you got fy of y to be 1 by 2, where y belongs to 0 to 2, right? So you can see that, so this is nothing but this whole thing is saying that your y is uniform in 0 to 2, right?
Ma'am, I got this approach.
Hmm.
Lekin, I mean, suppose that y takes some value, y is taking value equal to 2x, right? So for every
Okay,
value
yeah.
that x take, for every value that y takes, there is a specific value of x, right? So, but the probability
Yes.
will remain same. Only the value has changed, right?
Okay, can you repeat your question again?
So
We
suppose
have
that x
taken
is taking
capital
value.
Y. Huh.
Suppose x is taking value, some specific value, and y takes double of that, right? But suppose x takes value 5, right? When x
Okay.
takes value 5, y will become 10. But the probability with which x takes the value 5 and y takes the probability 10 will be same, right? Because y takes value 10
Okay,
only
okay.
when x takes value 5, right?
You are saying probability that x takes the value,
Some value
I mean,
is x.
fx of
X.
s5 is same as fy
A
of
5 of 10, value of 10.
10.
Right. Only the values has changed, right? The probability remains same. So only range has changed, the probability distribution remains same. Like we used to do na, in discrete random
Hmm,
variables. If
hmm,
x is
hmm.
taking some value and I have function of x, we also use this concept in finding the expectation of random variable, right? The
Yes.
probability was same, only the value has changed. So in the same way, we can directly say method.
Wait, but if you write fx of 5, this is also 0. Wait,
Y is
Fx
so
of
not
5
in
is
you
not
had
zero.
you had also changed the range for x. You're saying you had also changed the range for x.
Phi is not in the support
The
of
range is
this.
definitely different, man.
No, no, I mean the support of x. I mean, you have changed the support of x also. You're saying now that x lies between 0 to 5.
Yeah,
This is
I've
what
just
you're
given
saying,
an
right?
example. Yeah, yeah.
So you're saying x lies between 0 to 5, and now if y equal to x, your y will lie between 0 to 10.
Yeah.
Your y will lie between 0 to 10. This is 1 by 10. Okay.
Yeah. So now I'm saying
Let's
that
take,
Fy
okay,
will be
let's
just
not take 5. Let's take this as 2.
2. Yeah.
Okay. So you're saying
Fx
fx
of
of
Fx of 2 will be equal to
2,
Fy of
this is going to be 1 by 5. And what is fy of 2?
that is also going to be 1 by 5.
How it is going to be 1 by 10, right? It is 1 by 10 because we got it to be uniform.
But when probability used to remain same now, like I am trying to relate it to discrete random variable. If you remember, in trying to find expectation, we did
Okay.
this, right?
So you are
If
saying
x,
x is, let's say x is
suppose,
discrete.
But
yeah,
this is PDF, not probability. This is
This is
density.
PDF. This is
It's
density.
yeah,
density.
Yeah.
This is
that's
not
right. But
probability.
in small sense, if we take a very small length of interval, it can be modeled as that, right? Small, very small length of dx length, right? That's where all this
Okay.
concept originates from, right? So let's say, like for
Hmm.
discrete random
Okay.
variable, I'm trying to
Okay.
find a relationship between. Yeah.
So for discrete random variable, what you're saying, let's say
So,
x is discrete and it is taking the value, let's say 1, 2, and I'm defining y to be 2x. So your y will take the value
2 and 4.
2 and 4. The probabilities
Yeah.
will remain the same. So if it was
Yeah. So
1
if
by
you
2,
have PM
1
of
by
X,
again,
the same is PM of Y,
1 by
right?
4, 1 by 3 by 4. So the probabilities will remain the same for.
Yeah, yeah.
This okay. You're trying to say that even for the continuous case, the probability
Hmm.
should have been the same.
Yeah, yeah. That's what I'm trying to say. At least,
Uh,
like, not probability, but PDF at that point should have been.
PDF. Okay, so is there a generalization we can do here? Mm, see, definitely the PDF, as we saw this example, definitely the PDF is not coming to be same.
Mm-hmm. Yeah.
Yeah.
The PDF
Okay.
is changing.
Let's think about it a little more, and we'll see it later. Okay. For
So
now, we
that was
have an
probability and this
example.
is distribution.
This is
This is
just
density. This is
this we
density.
density
That
we are
was
talking about.
probability.
Yes, yes, that is right.
So density is different from
That
probability.
is correct. That is
So
correct. Uh,
density into the
okay.
value is giving the probability. It's the integration of
So
the
if we,
density.
yeah, if we do the integration of the let's say,
Density, but there should be some precise thing to it now because this is changed.
if we try
It's not well a
to,
precise answer, right? But it's density. That's not an explanation.
just hold on.
Yes.
Okay, we'll have to think a little more about this. Okay, let's skip this for now, but I will just write it here. Okay. The,
Excuse me, ma'am.
yes.
I have a doubt in the last step, ma'am. We have got
Okay. Hmm.
Fy of y is 1 by 2.
Yes.
Then, and hence y is uniform 0, comma 2.
Why is it
How it?
uniform 0 comma 2? So
Yes,
you
ma'am.
know that, okay, looking it's just by looking at the PDF function, but because if y is uniform in 0 comma 2, the PDF is going to come to be 1 by 2, right? For y belonging to 0 to 2. So it just by looking at this expression, we said that y is nothing but it is uniformly distributed in 0 to 2.
Oh,
Yeah.
okay.
Okay. Now, this was just one example. So, how do you generally find it? So, if you have any continuous random variable x, you have any continuous x is a continuous random variable, which has a CDF fx of x and has a PDF small fx of x. Okay. Now, you have defined a function of x. You have defined a function of x. Let's say g of x. All right. So let's say this g of x is another random variable that we denote it as capital of y. So how do you find this, how do you generally find this CDF? It's the same thing that we did previously. So we did fy of y. So this is nothing but probability, uh, this y less than equal to y, and this y is nothing but this gx less than equal to y, right?
So first we have to find a relationship between CDFs basically.
Yes, you have to find, like using the CDF approach, you can actually find the probability for the function of random variable. So it's like now you got probability gx less than equal to y, right? So if I let's draw, this is our x, this axis, and we have another axis, let's say g of x. We are saying, let's say gx is some equal to some y. Now let's plot some function we have. Okay, something we have, and we are saying probability, what is the probability that gx is less than equal to y? So when is gx less than equal to y? So basically all such x. So you see that for interval minus infinity, let's say some interval, it's just, let's say it goes like this. So from interval minus infinity to this particular x, you're saying that this gx is coming out to be less than equal to y. So basically this is same as finding the probability for such x such that such that your x should belong to such x such that your gx is less than equal to y,
Yes, ma'am.
right? So you need to find the probability for all such x. So in a way, what we have done is we have to find the probability that your capital X falls in all these intervals. Like so in this case, for this particular example, for this, let's say interval minus infinity to x. So if you find this probability, this will be equivalent to finding the probability that gx is less than equal to y. So this is the
Ma'am,
idea
can we
that
do
we
an
are.
example for this basically?
Yes, we are going to do. So this is just a general case when we are going to use the CDF approach. But there is one more easier method. I would say not in for all the examples, but if you have very complicated functions, then this becomes a little easier. So what this monotonic differentiable function says is, let's say you have a continuous random variable. Okay, let's say you have a continuous random variable x whose PDF is f of x. Now you have x random variable and you have a function of random variable g of x. So let's say this g of x is monotonic, and where should be monotonic? It should be monotonic in support of x. Okay, so let's say your function of random variable is monotonic in support of x, and
Support of x means,
it
ma'am?
should, support of x means what? Support you have seen in week 4, right? So basically the way you define support of x is,
PDF is greater than 0.
yeah, support of x is all such x such that fx of x is greater than 0.
Okay.
Okay, so we are saying for any random variable x that is continuous, if you have another random variable that is just a function of this continuous random variable, and if it is monotonic and differentiable too, so it should be differentiable basically, uh, then in that case you can define the PDF of y. Okay, we're going to define the PDF of y. How? This is going to be fx of g inverse of y divided by g dash of uh, g inverse of y mod of this. So if you are interested in this proof, we can put it on discourse. Okay,
Yes, ma'am.
like how this formula works and how it came, we can put it on discourse. Even I think if on discourse it is already there, but you'll have to look for it. So this proof how it came, we can put it out.
What is G inverse of Y?
Okay, so g inverse of what we said is, you have the random variable x and you have a function of random variable g of x, and we have said this g of, let's define this g of x to be y. Okay, so g inverse of y, you have studied the inverse function in maths 1.
X equal to G inverse of Y.
Yes, you have studied the inverse function in maths 1, right?
Yeah.
So it just that only, nothing special about it. So all right, so what we saw is we have we saw two different methods to find a distribution for function of random variable. So one general case you can do is that works all the time is using the CDF approach, and other is this monotonic differentiable function. If you have the function of random variable that is monotonic in support and it is differentiable, then we can define its PDF in this fashion. All right, now let's look at few of the examples. So how to check that? So the first example we have here is for the translation. So it's a very basic example. What we are saying is you have a random variable x, okay, that is continuous, and we have defined y equal capital X plus a, right? So this is a translation. All of you know that. We're just translating this random variable x with the constant a. So now how does the graph of, okay, before that, can you tell me if y is monotonic?
Yes.
Yes, ma'am.
This
Yes,
is
ma'am.
Yes,
monotonic,
ma'am.
right? Monotonic means in this case it is increasing function. So y is monotonic in support of x. So okay, here we should have mentioned that x belongs to R. Okay. Now using the monotonic differentiable function that says if you have a continuous random variable and you have if you have a function of random variable, so in this case it is x plus a, and this is monotonic in support of x, and y is differentiable. So you also know here y is differentiable, right? You can differentiate this y. Then you can easily find fy of y. You don't even have to go through the CDF approach. You can just write this as fx of g inverse of y divided by mod of g dash of g inverse of y. Can you mute yourself? A lot of noise is coming. So what is this g inverse of y? So we had y equal x plus a, and this is our basically g of x, correct? This is our g of x. Now what
Yes, ma'am.
is g dash of x? So to find to fit this into the formula we need g dash. So what is g dash of x?
1.
This is just
1.
1. Now we want what is g inverse
X equal to y
g
minus a.
inverse of y? G inverse of y is just y minus a, right? So if you put this into this formula, you get fx of what is g inverse y? It is y minus a. So you have fx of y minus a divided by mod of g dash of y minus a, right? Now what if you have if you had gx equal x plus a, g dash of x was 1,
It's
right?
always 1.
So it is always 1. So even this g dash of y minus a will also be 1.
It will also be 1.
So it is just fy of y is nothing but just fx of y minus a. All right. So this so if you have a translation function, if I mean if the function of random variable in if you're just translating, your PDF is just going to be fx of y minus a. So these are the things that you can also keep this in mind, like can also remember it basically. Like it can be quite useful in solving the
Ma'am, we
problems.
can, I mean, this translation we can find directly now
Hmm.
probability x less than equal to a by that.
That's what, like, yeah, that's why I had said initially that this will be useful. This monotonic differentiable function concept, it will be more useful when you have a very complicated function. But the cases like this where it's very simple function, it's easier to go with the CDF approach.
Yes.
Yeah.
Ma'am, is
Okay.
this like
Now
the,
what happens when you
is
have
this like an important part of the week? I mean, course, or the is
this
it is
is,
just
yeah, this is
given to add
important.
up to
This,
things?
it is, no, it is very important part of the week. All this function of random variable,
No, the this
function of random variable,
monotonic thing.
or monotonic differentiable function. Yeah, I mean, I said no. Like sometimes finding the CDF can be quite complicated. But if you know that your function of random variable, your g of x is monotonic, and it is differentiable, then it's much easier to find it. So sometimes it comes useful. You will once you solve the assignment problems, you will realize it. Like in few of the problems, this becomes quite useful.
Okay.
So it's good to keep this in mind. Okay. And how you got that proof? How do you got that FYOY? We'll put it on discourse. Now, we are going to look at the scaling part. So you have x to be continuous random variable, and you are defining your y to be a times capital X. Okay. Again, this ax is monotonic and it is again differentiable. So we can use the formula, and let's write it as g of x to be ax. So what is g dash of x?
A.
It is just a. And what is if this is y? So what is g inverse of y?
Y by A.
Y by a, right? So again, if you put this into the formula, you get in the denominator. In the denominator, you have g dash of g inverse y, that is y by a. Okay. And so if gx was ax, g dash of x was
Yeah.
just
Yeah.
the constant. So you take any x, your just derivative is going to come out as a. So even for this case, you will have in the denominator just mod of a. Okay. And so you will get the result fy of y
Ma'am, the
to be
denominator is g dash of g inverse y.
g
Yes,
dash of
ma'am.
g inverse y.
That is
Yes.
1 by a, no, ma'am.
Yes, ma'am.
What? Oh, why is it 1 by a?
G inverse y is y by a.
Yes, g inverse
Y
y
is y
is
by
y
a.
by a. So you
We
got g
want to
dash of y by
differentiate.
a.
G
You,
dash is 1 by a.
no, no,
Yes, ma'am.
no, no. You are not.
We have to differentiate this y by a, no, ma'am.
You have to
No,
differentiate
g
it with
dash of
respect.
y wave means g dash of x we have, and we have to put
Yes,
y by a at its place, at place of x.
yes.
It
G
comes
dash
out
will
So
to be
you
always
a.
be
had
So
A.
either way, it is going to be equal to a.
G
you
dash
had
will
g.
always be
uh,
A.
yeah, you had g of x to be a of ax. Okay.
Yes,
And
ma'am, that's okay.
when you did g dash of x, you got a.
Yes,
Now
ma'am.
what is this y by a? Y of a is just x.
Yes, ma'am.
Oh,
So you put any x there, your derivative is going to be just a, constant a. So that is why in the denominator you have this mod of a.
I don't
I
understand.
didn't get it,
Uh,
ma'am.
yeah, same
What,
here.
what I'm thinking is
Hmm.
we have calculated g inverse of y as y by a.
Okay, I think
What does it
what you're
mean, ma'am?
thinking
G
is
dash in the sense it is with
here you are
respect
not.
to x, huh?
Yeah, it is with that is right. It is with
Oh,
respect to x.
okay.
Yeah,
Uh-huh.
this is not your differentiating with respect to y. This is with respect to x.
Okay.
Okay. All right.
Ma'am, excuse me, ma'am.
Huh?
So in the formula, why isn't it g dash of x, gx in the denominator?
G dash of g inverse y.
Gx, only gx. Why is it g inverse of y? Well,
Ah,
because actually we have to use.
okay. Before this, like before we started this topic, I had mentioned we'll give you the proof of that formula on discourse. We'll put it there. You just check how this expression comes.
I'm still a little confused. We've
Yeah,
just said the G inverse of Y is basically the uh,
g inverse of y is y by a.
by A, right?
Hmm.
Which is the same as X, right?
Yes, yeah.
So the derivative of X would be with respect to this X, yeah, dx.
It just comes out to be a. You see here.
See, we have here we have three functions. First, we calculate g inverse of y, right? And we have fx. We have g dash. We have g of x, we differentiate it, we get g dash of x, right?
Hmm.
We have three functions. You must understand this. Like we have three different functions: g inverse of y, g dash of x, and fx of x. What we do is in fx of x and g dash of x, we replace x with g inverse of y. Whatever that function is, we replace x with that, and that is what is there.
Just think about it a little.
I'm not getting this. What we have is the G inverse of y is basically y by a, right?
Yes, this thing.
Which is the same as x, if I'm not wrong.
Yes, this is
Which
some
is
x.
x.
Yeah.
So if you're finding the derivative of x with respect
Any
to
x.
x, then it should be 1.
No. So you had, if you
May
have
I, ma'am?
defined your
That y by
okay.
a should be equated to x. So y
Yes.
becomes ax. Okay, when you differentiate ax, we'll be getting a. That's what I understood. Am I right, ma'am?
Y
Okay.
equal to x is given
No.
only. Now we are going in opposite directions.
See, you are. It is already given that g of x is a of x. Okay.
Yes, ma'am.
And if you differentiate this function with respect to x, you get a.
That's fine, ma'am.
Okay.
That's correct. Yeah.
Now you have g dash of y by a,
Yes,
which
ma'am.
this is
Yes.
nothing but a particular x. Okay. And from here you can just say that any x you give, the derivative of gx with respect to x is going to come out as a. So this g dash of y by a is nothing but a.
Yes, ma'am, clear.
It is
Yes,
clear.
ma'am.
Just if it is not clear, just think about it a little. You can go back to your
We
inverse
put the
function.
value of g dash x is equal to a. Okay,
G
g
dash of
dash
x.
g
Yeah.
inverse y is equal to y by a, which is equal to x, and g dash
Huh.
x is value is a. So we
Yes.
put the value of a.
Yes. If it is not very clear, I would suggest you can go to the inverse function part and just try to understand. Okay. Now we looked at translation, we looked at scaling. Then we have a fine transformation, that is nothing but just ax plus b. I would suggest you to just do it yourself. Okay, it's the same thing, the same process. You will get the final result as 1 by mod a fx of y minus b by a. Just
May I
try it out.
request something in the scaling one?
Okay, yeah.
We just did earlier that y is equal to 2x. I believe that was a scaling.
Yes.
Could we please do that using that formula?
Okay. Okay. So we had x that is uniform in 0 to 1. We have y equal 2x. Okay.
Yes.
Now you just write g of x equal 2 of x, and this is just y. Okay. So what is g dash of x? This is 2. What is g inverse of y? So
X by 2, y by 2, y by 2.
y by 2, right?
Yes, ma'am.
Now what is g dash of g inverse y? This is nothing but g dash of y by 2. And what
Yes,
is
ma'am.
g dash? This is just going to be 2. Okay. So using the formula, we can say fy of y is fx of g inverse y, that is y by 2, divided by mod of 2. So it will be just 2, right? And what is fx of y by 2? It is so 0 to 1, right? Yeah. So 1, 1 by 2. So you got fy of y to be 1 by 2. So again, you can say that y is uniform in 0 to 2, right?
Ma'am, g dash of pi by 2 is 1 by 2, right?
Uh, Again, the same question you asked.
Same problem.
This is not with respect to y, this is with respect to x.
It's
J
like
is a function
saying
of x.
independent variable in that function is y by 2. So y by 2 into a and then derivative, right?
First, we are derivating it with respect to x, and then we are putting y by 2 at the place of x. That's what we are doing, right, man?
Yes, yes.
How is the numerator f? What is the value of numerator? How is it 1?
Where? How is it 1?
Yeah.
Because you have fx of y by 2.
Hmm.
And what is x? How is x defined? X is uniform in 0 to 1.
Yes.
So fx of x is going to be just 1. And what is this y by 2? This is just x, right?
Yes.
So any, and you know that support of x is just 0 to 1. So whatever x you take between 0 to 1, it's just going to give you 1.
Okay. Actually, the uniform distribution is a very strange one. It's just 0, 1. Okay.
Yeah.
It's confusing. Okay. Thank you.
You see that you got the same answer.
Yeah.
Yeah. So, all right. So we have skipped this affine transformation. The same way we have done the translation and scaling. You try for affine transformation. Okay.
It's very easy, man. You can do it.
It is easy only. So even for normal distribution, it's just special case of that affine transformation. So I will just go through the result. The derivative part you can just do it yourself. So what
Will this
this
be
will be
PDF be
provided to you.
available?
This,
Yeah.
yeah, by tomorrow or Monday it will be available on the portal. Okay. So I will just write down the result here. So the first result, yeah, who is there? Okay, the meeting is not getting streamed on YouTube. So I'm recording the session and we'll put this on the YouTube. I think there's some issue there.
Yeah,
All
ma'am,
right.
I'm previously meeting is not on YouTube.
Yeah. All right. So I'll just write on the result. The derivative part you can do it yourself. So the first, what it's saying is, if you have any normal distribution x with the mean 0 and variance 1, and you define another random variable that is uh, written as a sigma of x plus mu. So this is an affine transformation, right? So its distribution y will come out to be normal with mean mu and variance sigma square. So if you have a standard normal distribution, you and then you do this translation, not translation, this affine transformation of x, that is sigma x plus mu, then your y comes out to be a normal distribution with mean mu and variance sigma square. And the second result says, if you have a random variable x, just the opposite of it, if you have a random variable x that is normal with mean mu and variance sigma square, and you take another random variable y which is a function of x, and you define it as x minus mu by sigma, then y comes out to be normally distributed with mean 0 and variance 1. So these are the two results that you will get from here. Okay. You
Ma'am,
can try it
just
yourself.
one question here.
Yeah.
In this course, when we talk about a normal distribution,
Hmm.
second parameter of the normal distribution will be sigma
Sigma
square
square.
or
Sigma
sigma.
square. Sigma square.
Suppose it is given as phi, then sigma should be considered as root phi, right? Because in
Yes, yes, yes.
many of the
If it is
examples,
normal 0, I remember that part.
in many of the
But
examples,
But later, sir has corrected it.
okay, so it is always sigma square.
It is sigma square. Yeah.
Okay, so if it is given as phi, suppose 0 phi, then we have to
Then
take
you
sigma as
0
root
root
phi.
5 square. Yeah.
Okay.
All right. Let's move ahead. All right. Now we are going to look at some of the problems. Let's do the problems. Uh, all right. First, I will not show you how to do it. Can you try it yourself first? This problem.
Yes, ma'am.
Yeah, I will just give you 5 minutes to do it. Okay. So you can use any method that whatever you like. So you have a random variable x that is exponentially distributed. I will just write down what is the PDF of x here. So it is just going to be lambda e to the power minus lambda x for x greater than 0. Okay. So now you have to find
Greater than
the
equal to 0.
okay. Doesn't matter. It's okay. I'll just give you 5 minutes, and later I will ask you the solution. I would suggest all of you to please try it yourself first. Yes. Do you have any doubt?
No, ma'am.
Okay. Yeah. Okay. Any answer?
1 by mod of 2 root.
1 by lambda square.
1 by lambda square.
1 by 2 root y lambda e raised to minus lambda root y.
Wait, can you repeat again? What is 1 by lambda square? What is your answer? Can you repeat again?
1 by 2 root y lambda
Okay.
e raised to minus lambda root y.
Minus lambda root y.
Huh.
And how? Where does y? What is the range of y?
Greater than 0.
Okay. So you're saying fy of y is this. Okay. Any other answer? Anybody else?
I'm not sure. I'm just trying.
Yeah. You can try.
1 by lambda, I'm not sure, but it's 1 by lambda, I'm not sure.
1 by lambda.
Yes.
So you're getting fy of y to be 1 by lambda.
Ma'am, e power minus lambda y
E to the power minus lambda y.
minus e power lambda y whole into lambda.
This one, this answer.
No. A minus
Minus
e power lambda y.
e to the power lambda y
It's and whole into lambda. That
whole into lambda.
whole this whole expression into lambda, and
Okay.
the first e power minus lambda y doesn't have lambda. First G.
So
Yes.
you are saying e to the power minus lambda y minus e to the power lambda y whole into lambda.
Yes, ma'am.
Can I
The
give
middle.
mine?
Okay, yeah.
Lambda e to power minus lambda x
Lambda e to the power minus lambda x
by x.
by x. Okay. Anybody else?
Yes, ma'am.
Yeah, please go on.
Minus 1 by 4
Minus 1 by 4
y root y means
y.
in denominator.
Okay. In denominator we have y root y.
Y root. Yes, ma'am.
Okay.
Plus
Plus
1 by
1 by
2 y root y
2 root y.
2 y root y in
Okay.
denominator
Okay.
into e to the power lambda root y
Into e to the power lambda root y.
lambda root y
Okay.
and plus
Oh, okay.
it is one more term plus 1 by 2 lambda root y
Okay.
into e to the power minus lambda root y.
It's quite a big answer. All right.
Ma'am, this initial e also has negative power.
Okay. Anybody else? Any other answer? No. So we got one. This is the first. Second answer. This was the third answer. Fourth answer, and five. We got 5 different answer. So I would ask, how many of you got the first answer? Many people raised hand. 1, 2, 3, 4. Okay. 6 people has gotten, one as the answer. All right. So how many of you got Fy of y to be 1 by lambda?
No, I was mistaken there. It's not 1 by lambda, ma'am. I'm recalculating it. It's
Okay.
not 1 by lambda.
Okay. All right. Who else has gotten e to the power minus lambda y minus e to the power lambda y whole lambda? Nobody? Only one? Okay. Okay, this is definitely not correct because this is in terms of x. I had asked for Fy of y. This is wrong. This again looks very complicated. Let's see which one is the correct answer. Now, okay, you were given to us x equal. Let's see what is the answer, the final answer. Okay. So the final answer is 1 upon 2 root y lambda e to the power minus lambda root y. So looks like the first one is the correct answer. This is the correct answer.
Yes, ma'am.
Yeah.
Yes.
Yeah. All right. Let's look at how did we solve it. So we had y equal x square. Okay. This is and we had to find the CDF for this function y equal x square. So Fy of y is again probability y less than equal to y, and this is just x square less than equal to y, and this probability x square less than equal to y, this is same as probability that x is less than equal to root
Root
y,
y.
right? And this is just fx of root y. And fx of root y is just
lambda raised to minus lambda root y.
lambda e to the power minus lambda.
Ma'am, fx
Uh,
is
fx
CDF, na ma'am.
CDF. It
CDF
is
is
CDF. It is
one.
one minus.
Yeah,
Okay, there is a mistake here. 1 minus
e to the power minus lambda x it is.
1 minus e to the power minus lambda root
Lambda.
y.
Yes.
This is what you get. Now you differentiate it. So once you differentiate it, you will get this has to be corrected, right? Just mark it here. This is wrong. Okay. So what is the differentiation of 1 minus e to the power minus lambda root y? It is going to be,
Ma'am, before differentiating, can we check this relationship using monotonic differentiable functions?
okay, you want to check this first monotonic differentiable function. Okay. So you had x to be exponential lambda and y to be x square. Okay. And the support of x is positive, right? Because it's exponential. And in this support, this is
It is monotonic.
monotonic, right? This is increasing basically. So we can use the
Yeah.
monotonic differentiable function. All right. So y equal x square equal to g of x. Okay. So what is g dash of x? It is 2x. And
Yes,
what
ma'am.
is g inverse of y? It is root y.
Root y.
Okay.
Yes, ma'am.
So fy of y is fx of g inverse y, that is root y,
It's yeah.
divided by uh,
G,
mod of
G dash of
g
G
dash
dash
of
mod
of
of dash of
root
root
y.
y.
root y.
Okay? And fx of root y is what? This is going to be
Lambda
lambda e to the
lambda
power minus
minus
lambda
lambda root y
No,
root
ma'am.
y,
divided by 1 by
yes, divided by
2 by
Ma'am, CDF we are using wrong, na ma'am.
CDF. We are not using CDF, we are using PDF, right?
This is a direct relationship between PDFs.
Yes. I think okay. I think you thought this was for CDF, is it?
Yeah, I thought it is the relationship between CDFs, and then I differentiated it to find the relationship between PDFs.
That's why you got very complicated
Such a
answer.
long, it's a, yeah.
So fy of y is lambda by 2. So this is the correct answer. And even if you use the CDF approach, so you have to differentiate 1 minus e to the power minus lambda root y. So you will get what? You will get differentiated. So minus e to the power minus lambda root y and divided by minus lambda, and root y is again 2 root y. So wait, I will just clear some space. Okay, so what is the derivative? It is
Into
uh,
minus
E to the
lambda
power
by 2
minus
root
minus
y.
lambda
lambda,
root y.
you have 2
2 root
root
y.
y. Yes, again you'll have
And one
minus.
more minus is there. Yeah. Yes, ma'am.
Yeah, one more minus is there, right?
Now one more
So it will
lambda
become
below is
plus.
there because lambda root y, na ma'am.
No, lambda is not there. No, you had to differentiate this 1
Yeah, yeah.
minus e to the
So,
power
yeah,
minus.
yes, 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 yes.
Yeah, right. Okay, so this is the answer you got for using both the approach.
Ma'am, in the
So
above, is it not 1 minus e power you rounded with red color? Above to that?
that is wrong. I mean, here it has been written as PDF, but actually we are writing writing CDF, and we have written this PDF here.
Yes, ma'am.
So this is wrong. That is why I marked it as red.
That PDF is 1 minus e power minus
Yeah,
lambda root
1
y.
minus e to the power minus lambda root y, and now you will have to differentiate
There is
this.
no lambda, ma'am.
No. There is no lambda. So what you will have is you had if like look at from this step. So fx of root y, right? So
Yes,
you
ma'am.
know the CDF of x is given by lambda e to the power minus lambda
Minus
x.
lambda x. Yes,
So
ma'am.
lambda e to the power minus lambda, in this case it is root y. Okay.
Yes, ma'am.
Now to find the PDF, you will differentiate. Uh, Sorry, again I wrote the wrong thing.
Yes, 1 minus.
Yeah, it is 1 minus. This is CDF is given as 1 minus e to the
CDF
power minus
exponential is
lambda.
1 is lambda
Yeah,
x, and
exponential
we
is
have to
1 minus
differentiate
e to
between.
the power lambda x.
Yes, ma'am. Yes, ma'am. Now I got it, ma'am.
Yeah, you got it. Yeah,
Yeah.
this is
Differentiation.
wrong here.
Yes, yes. Thank you.
All right, so okay, this seems to a major problem. How many of you have seen this problem in lecture? Since none of you are told you have watched the lecture, I would expect very few people to answer this. Has anyone seen this problem?
No, ma'am.
No.
Yes, ma'am. Yes, I
No,
have seen.
ma'am.
It
Do
could
you
not
want to?
clear to me. This
Sorry.
one and next one.
Okay. You couldn't understand.
Yes, ma'am.
All right. So I will solve this problem here. Or do you want to try first for some time?
I'll try.
Yes, yes.
Let's
Ma'am, we
take
will try.
just take 2 minutes to think about this problem.
Yes.
Then I will ask you the ideas for this. Okay. Just take 2-3 minutes to think about this problem.
Ma'am,
Mhm.
this will not be a monotonic function, right?
Yeah, this is not monotonic in support of x, right? This is a good point. I'll just write it here.
What is the consequence of that?
Because if
You cannot use that
yeah, you
monotonic
cannot
formula, no?
use that formula.
Okay.
All right. So should we look at the proceed with the solution? Any ideas? Anyone wants to tell?
And the range of y will be from 0 to 1.
Okay, so
0
you
to 9 minus c square is 9.
range of y is, what did you get? One person said 0 to 9.
0 to
Somebody
1.
1 to 9. 1 comma
It's
9.
1 to 9.
1 comma 9. Okay. Any other answer?
And 0 comma 1.
0 comma 1. Anything else? No? Okay, let's see what should be the range of y. Okay.
There
It is
is
clear.
like, if,
Sorry.
ma'am, if I say like, if I define the function for y, right,
Huh?
and I say y is in this range, suppose I say 0 to 9, right,
Okay.
and now x takes value 2, then y is 4. But
Hmm.
for x equal to 2, PDF of x is 0, right?
For x equal to,
PDF of x is 0, right?
no, right? X equal to 2. PDF is what? PDF is 1 upon 4, right?
But minus 3 to 1, it is 1 by 4. No? For x equal to 2, I
Minus
know.
3 to 1. Yeah. Oh, you're saying x equal to, not minus 2.
Yeah, x equal to
For
2,
x
I know.
equal to 2, yeah, it is 0.
So, and for x equal to 2, PDF is 0. So, y's PDF should also come out to be 0, right?
Y PDF should also, yes.
Yeah. But if I say x equal to 2 and I square it, so I get y equal to 4.
Okay.
So, and
Mm-hmm.
so if I say for y equal to 4, I am defining, then I don't
Hmm.
know how I'm getting that 4. Either it's minus 2 ka square or 2 ka square.
Yeah, both are possible. I mean, you know that x is lying between minus 3 to 1. So if you are getting x square to be 4, then definitely it cannot be for x equal to 2. It is going to be for x equal minus 2.
So how can I define my function for y if I like?
Okay. So first of all, you all are convinced that x square is not monotonic in support of x, right?
Yes, ma'am.
Yes, ma'am.
All right. So we are not going to look at this method. All right. Now let's move to how do we approach it using the CDF approach. So let's see this figure. You have x here and y equal x square. So you have this y equal x square. Okay. And x lies between minus 3 to 1. So let's take it as minus 3 and let's say this is R1. So you know the PDF is going to be 1 by 4 for this range. All right. Now what happens? So if x lies between minus 3 to 1 and y is defined as x square, so what is, from minus 3 you will get 9 and from here you will get 1. Okay. So some of you have said that range of y is 1 comma 9, but you are missing this point that x lies between minus 3 to 1, so you also have 0 here, right? So you also have 0 here, so if you square it again you're going to get 0, so you will have to add 0 to 9 here. So range of y is 0 to 9. Is it clear why the range is 0 to 9?
Oh, we need to compare the range of x as well as the range we get from y.
If it is 1 to 9, we are not getting that 0 to 1 part.
Yeah, if you are just taking 1 to 9 you are not getting this part.
0 to 1 part. Yes, ma'am.
Yeah, simply that part. So range
Oh,
of y will be 0 to 9. So since x equal minus 3, let's say this is our 9. Okay. Let's say this is our 9. Now what happens? Now how will you find the CDF for this? Okay. Let's see. So this is just minus 1. We have a figure here. We don't have figure. Okay, so how do you find the CDF? You know that y belongs to this 0 to 9, all right? So if you take any y that is less than 0, for this fy of y is 0, this is right.
Yes, ma'am.
Yes.
Yes, ma'am. Yes, of
Now
course.
if y lies between your 0 to 1,
Yes, ma'am.
why we are taking it as just 0 to 1?
Because from -1 to 0 and 0 to 1 we
Because
have
we have repetitive values.
One by one you can say.
from -1 to 0 and from 0 to 1 we have the same value of y from 0 to
Okay.
1.
So we can look at what happens when y lying between 0 to 1. Okay. So in this case, our fy is just probability capital Y less than equal to y, and y is x square. So probability capital X square is less than equal to y, and this is same as probability that x is. Okay. So in this case, it is going to be x lying between,
-5 and
yes,
minus
minus
root
root y
Minus root y and plus root y.
plus root y, right? And this is going to be
Yes,
fx of root y minus fx of minus root y. So what is fx of root y here? X is
y plus 3
uniform
by root y plus 3 by 4.
root. Okay, you got root y plus 3 by 4. And what is fx of minus root y?
Minus root
Minus
y
root y
plus 3 by 4.
plus 3 by 4, right? So if you solve it, you will get
2 root y
2
by
root y by 4. So this is what we got here
ma'am.
also.
Ma'am, that fx of root y I got.
Huh?
After that, that you are putting value in the function, na, that depends on the value of root y. If root y is was 4, right?
Huh?
Root y cannot be 4, right? Yeah. Root y cannot be 4.
No, what you're saying?
I'm saying if root y takes some value like which is not in the range of x.
We are taking y for 0 to 1, right? We are
Yeah, we
taking
are
y
taking y
between
for 0 to 1.
Okay,
We
okay.
are
For
only
0
talking
to 1,
about
we are
this.
solving.
Yeah, so if you look at any y that lies between 0 to 1, uh, it's just going to give you some minus root y to root y. Okay.
Yes.
Ma'am, where
Ma'am,
it comes 3 by 4?
ma'am, can you explain root y plus 3 by 4? How did that
Okay.
come?
So x was uniform in minus 3 to 1. Okay. So you know that in case of a uniform distribution, your CDF is given as x minus a upon b minus a, right? So x in this case is what? Root 3. Sorry, root y. So x minus a upon b minus a. Okay. So x in this case is root y minus a. A is minus 3. So it becomes plus 3. B minus a. So 1 minus minus 3. That is 4. Same thing we did for minus of root y.
Okay.
Okay.
now to find PDF we have to differentiate it, right?
Now you have to find this PDF. You'll have to differentiate it.
Why
Right.
did we take? I didn't get. Why did we get take y's ranges between 0 and 1?
Not we didn't get y between 0 to 1. We got between 0 to 9. Now we
No,
are finding it separately.
yeah, but you determined separately for the range y being between 0 and 1.
Okay, see
I
what
said,
happens, huh?
yeah.
What happens is like if you take let's say y line between 0 to 9 itself. So you see that if you take any line here, it is going to be from minus root y to 1 only. Minus root y
Ma'am,
to 1. But if you take
ma'am,
it,
like we can also see like the way we have progressed in the equations now,
Hmm?
where we got fx of root y minus fx of minus root y, right?
Yes, yes.
Now, if I want to use this formula, it is only applicable if x lies between minus 3 to 1, which means root y lies between minus 3 to 1. Now, root
Yes.
y is positive definitely, so root y should be between 0 and 1, right? Then only can I apply this formula.
Oh,
Like
No, I
this
I didn't get what
expression
you
that
said. Huh.
I'm
Repeat
saying,
again.
this
Hmm.
expression of this CDF function
Hmm.
of
Hmm.
x, x
Hmm.
minus a by b minus a, this
Yes.
is only applicable when x lies between minus 3 and 1, right?
yes.
Hmm.
Now I have fx of root y minus fx of minus root y. Now at the place of x I have root y. So if I want to use this expression, then root y should lie between minus 3 and 1,
Hmm.
right?
Hmm.
And root y is definitely positive, so it should lie between 0 and 1. And so
Hmm.
root y can lie between 0 and 1 only when y lies 0 and 1. So this expression can be used only when you lie between 0 and 1, right?
Hmm. Yeah, that is right.
So we can think, if we want to use this expression, we can think, we can solve a
Yeah, see, uh, why did we take it from 0 to 1? Okay, let's say I took it for, let's take some other color. Let's say I am defining it for y 0 to 9. Okay, let's say I took this. Now I draw any y. Okay, let's say this is some y. So in this case, your probability x square less than equal to root y, this will become probability that x lies between minus of root y. It can go only till 1. Like the upper limit will be 1. So for we'll have to separate this for the y lying between 0 to 1.
Do we have to take only positive values of the square root?
Positive value of the
Is that
square
what
root.
we're saying? I don't understand.
What do you mean by positive value of square root
I mean,
here?
I still don't understand why the 0 to 1.
Okay, we go to this, let's try to find for f y lying between 1 to 9. Okay, what
Okay.
happens in that case? Just note this. So what happens when, let's say this was r1, this is r1. Okay, now if you take any y that lies between 1 to 9, okay, then fy of y will be probability that x square is less than equal to y, and this is going to be probability that x lies between minus of root y. It can go maximum till 1, right?
Yeah.
Right. So in this case, your pdf will change. So what is going to be the pdf? Again, you will just differentiate your uh just look over here. So okay, here also it has to be changed.
What we just stated was
This one,
CDF, right?
sorry.
What we just stated was CDF, right?
Yeah, this is cdf.
Yeah.
So we got probability x lying between minus root y to 1. Okay,
Because, yeah, okay, X cannot exceed 1.
x cannot exceed 1, right?
Okay, so root Y should not exceed 1.
Yes, that is a upper limit that you have for one x. So how do you find this probability? So one way that we saw previously is you can do fx of 1 minus fx of minus root y, but you can also do it using integral fx x, again here it is dx, again here it is dx. Okay, so minus of root y 1. So what
Okay.
is fx of x? It is just 1 by 4, and you will get 1 by root y plus 4.
It's 1
So
by.
you
Okay.
yeah, so you saw that for when y was lying between 0 to 1, your CDF was root y by 2.
Sorry.
When I will write it here. When y was between 0 to 1, yeah, so when y was between 0 to 1, your fy of y was root y by 2. Okay, now when for y lying between 1 to 9, your CDF is 1 plus root y by 4. Okay, now you have to find the PDF. So to find the PDF, you'll have to differentiate. So for y lying between 0 to 1, it is
1
what?
by 4 root y will be in the denominator, right, ma'am? Here. Root y
Root
will be in
y.
the denominator.
Yeah,
Okay,
ma'am. For
what
0
was it?
to 1, it's 1 by
1
4 root y
by 2 root y
into 1 by 2.
into 1 by 2. 4 root y. Okay, okay. Yeah, this is wrong.
And even in the second one also, root y will be in the denominator.
Okay, yes.
Ma'am, and integral limit is minus square root of y to minus 1, right? Because we already included minus 1 to 1 in the first case.
What you're saying? You're saying integral limit is
Minus square root of y to minus 1.
This
minus
is
1,
CDF.
not minus 1, right? It is 1 because you're finding
This is
CDF.
CDF.
CDF. This CDF we are talking about here. You're finding the CDF, right? Y is lying between 0 to 9. This is the CDF we are finding. So your x should be between minus root y to 1. Okay, this part is wrong, no? Okay, I'll just change it. Okay, any doubt in this?
How did we get by being 0 to 1 being this FYY root y? I got the 1 to 9. This one I understood. We've just found the CDF as 1 plus root y
Hmm.
by 4.
So for 0 to 1, you will have, you see here, that for when y is lying between 0 to 1,
Yeah.
let's try it here. So it was minus, say this is minus 3 and 1, okay?
Yeah.
And this is x square. Now this is 1 by 4 and this is 0. Oh, this is not actually right. Let me draw the figure properly somewhere. Yeah, minus 3 to 1. So this is your 1. Okay. So this is your y. Okay. Let's say this is 9. So for any y that you take between 0 to 1, right? For
Yes.
any y that you take between 0 to 1, say this is a y. Okay. So you see that This is lying between minus of root y to root y, right?
It's minus 1 to 1, positive 1.
Right? If you take it between 0 to 1. So this is what we have done.
Okay.
Yeah.
So will we combine these now then?
Combine what?
So we have from 0 to 1 and we have 1 to 9.
So if you have to, let's say, if I want you to write fy of y, what you will write? You will write it is 0 when y is less than 0, right? And it is what? It is 2 root y by 4 is 2 root y by 4 when y lying between 0 to 1, and it is 1 plus root y by 4, 1 plus root y by 4 when y lying between 1 to 9, and it is 1 for y greater than equal to 9, right?
Ma'am,
This we were supposed to find CDF or PDF?
No, we are supposed to find PDF. So this is a
Yeah.
CDF I
So
have written. Now if you have to find the PDF, you will differentiate this function to get the PDF. This what you have seeing here on the screen for PDF is wrong. I will change it. So you just have to differentiate this.
okay.
Okay.
We just have to differentiate these with respect to y.
Yeah, with respect to y.
Okay.
ma'am,
It's a little
Yes.
complex.
Yeah, it's a little complex.
ma'am, am I audible?
Yeah, you're audible. Tell me.
Yeah. So I have one doubt. Suppose
Mhm.
x is 2, right? Then PDF is 0, right?
If x is 2, okay. Yeah.
Then
If x
PDF of
is
x is 0.
2, huh? Fx of
PDF of x is 0.
x is
Yeah.
0, right?
Yeah. So f of y should also be 0.
F of y should also be 0, right?
But how does the PDF that we are getting captures this thing? Because
How is the PDF that we are getting captures this thing? Yeah, so what we are
if we
saying
take x
is,
equal to 2, then y becomes 4 now, and for 4 it is giving the value, right?
uh, no, wait. So we got our Fy to be 1 by 4 root y when y lying between 0 to 1. We are getting this to be 1 by 2 root y into basically 8 root y for y lying between 1 to 9, 0 otherwise.
Yes, ma'am.
Yeah. So this
Now
is a
when
PDF for y.
yes,
Huh.
now when x takes the value 2,
Huh.
then y can take the value 0, right?
If
F
x
of y.
takes if x takes the value 2, definitely y is 0 in that case. Yeah.
Yeah, but does our PDF this PDF captures this thing in any way? Like for
But
if
ma'am,
y is
But
4,
x,
then
when
it
we
is
take x2, it's coming out of the range, right?
ma'am,
Yeah.
but when x is equals to minus 2 is contributing for fy is equals to 4.
Y equal 4. Huh.
yeah. So for y equal to 4, it is giving value, but it does not capture it that if x comes, it comes from x equal to 2 or x equal to minus 2, right? So
I mean, okay. So what we saw there when we're talking about the CDF approach, we had said if we have any general uh, g of x and we want to find the PDF, find the CDF. So basically, we looked for all that set for which all those x, right, for which gx was coming out to be less than equal to
less
y.
than, yeah.
Now in this case, our gx is x square, and if we are taking so if I'm saying my x square is less than equal to some y, okay, and this y if lies between 0 to 1, then we are finding that probability is equivalent to finding the probability that x lying between this minus root y to root y.
Yeah.
If we are finding the probability CDF that x square is less than equal to y when y is between 1 to 9. So when y is between 1 to 9, so if we take any y here, okay, so you have to find uh, all such you have to look for all such x for which your gx is basically x square is less than equal to y. So this is happening for only minus root y
Yeah,
to
it is
1,
happening for. Yeah.
only for minus
But
root
if
y to
someone
1.
looks at that function, the person cannot tell, right?
uh, but
It should be like somewhere pointed out, like in some way.
this you are getting from like x square, right? I mean, using the CDF of x, you are getting the CDF of y
Why?
basically. So going from here to there, I mean, okay, any thought on this?
I didn't get the question.
Okay, so his question is like, if we look at this PDF of y, uh, how do we get that? What is the uh, range of how will you get to know about x basically using this y? Not sure if we can do that from here.
Maybe because like we are trying to represent a PDF of y in terms of y, right? Not in terms of x.
Yeah, right.
We are taking our x
So
between
y
-3 and 1 only, na? We
minus
are
3
not.
and 1 only, yeah.
Yes. So we
What
are
if I
not.
show this function to someone?
So
Like,
y equal
you're
x
getting my
square.
point. Like some information is getting missed in between. Like
Okay, so
loss of information
for
is there.
y lying between 0 to 1 and y is x square, so basically y is going to be x square. So x square lying between 0 to 1. So you're saying x lying between minus 1 to 1 basically here, right? Right. So if you look at the first one, we are
It's
saying that
perfectly
for
right.
x lying between minus 1 to 1, you have 1 by 4 root y. Okay.
Yeah.
Now, if you look at the second one, you are saying is x square lying between 9 to 1,
Which implies that
1 to
x
9,
lying between
which implies that
-1 to -3 and 1 to 3.
-3 to -1 and 1 to 3.
Yeah, -3 to -1
minus
and
3
1
to,
-1
yeah.
and 1.
And we can
1 to 3 is not
discard
in
1 to
the
3.
1 to 3 is not in the support of this function, yes, right?
Yes.
It is
So,
not, but it should be somewhere like captured in this new function that we are creating. This thing should be there. Now we are losing information sometimes. We add something and now we do not.
Anyway, probability of that is zero, no?
Yeah, probability of that is zero. But what is trying to say that if we have the PDF looking at this, we are not able to capture this information that x is between -3 to 1, basically. Okay, let me think about it a little, and I will post this problem on discourse also about this. Okay,
Could you just scroll up?
scroll up. Okay, yeah.
When it was 0 to 1, we found
Okay,
fy of y to be 2 root y by
by
4.
4. Hmm.
And then to find the PDF, we differentiated it.
Hmm.
I was just thinking we first found the integral, then again, whatever we got, we found the differentiation. And why didn't it come
No,
to
no,
the
no.
same? That's why I got confused.
No, Fy is this part, right? If you want to find the probability, you can also do it using the PDF. So if you have to find probability that a line x line between a to b,
Yeah.
so this you can, and you know if x is a continuous random variable with PDF fx of x, you can write this as integral fx of x. You can integrate your PDF over the interval ab,
Yes,
right?
that I'm aware. Yes.
So this is what we have done here. So we know x is uniform random variable with -3 in -3 1. It is 1 by 4 dy, and you just put the limit, and you got this.
Yeah, I was actually thinking that we just found the integral and then we differentiated the integral. Then why wasn't it coming to the same thing?
No, this is for this you have written for fx of x, right? Means PDF of x, not PDF of y.
Okay,
Yeah.
that's fine.
Ah, okay. Let's move ahead. So the next question. Uh,
Ma'am, the confusion. Can we differentiate the CDF of integral? Sorry, integral the
can
CDF.
we differentiate what?
Sorry, integral the CDF as you wrote to our
No. What?
x minus root 5 to
Root y by 4.
root.
This is what we got.
Yes, through integration.
Okay. This is
This is
RFY of
CDF.
y. This is CDF of y. Now
Yes,
you know the relation between PDF and CDF is that Fy of y
different.
is integral of Fy of PDF of y dy. So if Fy is differentiable, so if you are able to differentiate this Fy, okay, and this will give you PDF of y. So we are differentiating this to get the PDF of y. We are
See, ma'am,
different.
it's can you scroll up?
Okay. Hmm.
In this from 0 to 1,
Hmm.
you differentiate here, you integrate here minus root y to y 1 by
Hmm.
4d. That's
Yes.
why I'm asking.
Okay.
So this is, Acha, you wrote it above PDF form.
Yes. Yes. PDF of x.
Okay.
Let's try. Just try to do this problem again on your own. Currently, I have done it, but just try to do it yourself first. Again, this problem. Okay.
Okay, ma'am.
Yeah. Just clear this part. So
Ma'am, this is
this.
also very confusing, max of x and
Okay.
This has a lot of maths,
yes,
Yeah.
fractions, inverse,
You're
and
going to get a lot of
differentiation,
math
integration. Yeah,
till week 6. You're going to get a lot of math. Yeah.
I have to remember all the concepts.
Okay. So what will you do in this problem?
find the PDF of max x comma 0.
Yes, that is the problem, but how will you do it? All right. So you see that again x is uniform in -3 to 1. Okay. And you have to find the PDF of max of x0. Okay. Now just look over here. When x lying between -3 to 0, right? When x is between -3 to 0, how is y defined?
0 is 0.
It is, yeah, it is defined as maximum of x0. So it is going to be 0. Any x that you take between -3 to 0, your y is going to be 0, because maximum is always going to be 0, right? Right?
Yes.
So y
Yes,
is
ma'am.
Yes,
going
ma'am.
to be 0 for any x that lies between -3 to 0. Okay. Now when x lying between 0 to 1, when x lying between 0 to 1, what happens?
Max is 1. Y is equal to 1.
Max varies between 0 to 1.
Right? It is maximum is going to be 1. So basically your y is varying from 0 to 1. So just right here, y is varying from 0 to 1. Now again for y less than 0, this fy of y is going to be 0. Okay. Now you have y lying between, what happens when y lying between 0 to 1? Okay, so let me draw this figure again.
Ma'am, for x 0 to 1, y is
Mhm.
equal to x, no?
For, sorry,
For x 0 to 1, y is equal to x, no?
ah, y defined as maximum of x0. Yes, yes, yes. Yeah, thanks, thanks. Maximum of x0. So it is x, right? Okay, let's see here. So for y, when y is less than 0, okay, you know that range of
Yes,
y
ma'am.
is 0 to 1. So for y less than 0, fy of y is definitely going to be 0. Okay. But what
Range
happens
of phi,
when,
ma'am, 0 to 1 is given to us.
no, this is what we found just now, right?
Okay, okay, okay. Got it, got it. Yeah,
You got this is what
yeah,
we found.
yeah.
Since it was y equals 0 for x lying between
Yeah, less
-2
than
to
equal to
0,
maximum it can go to is 1 only when x
yeah,
equal to 1.
yeah, it can go to 1, right? So for y less than 0, it is 0.
Y
But
could be -2 also. No?
y can be, sorry,
-2. -2. If
y can be
and,
-2. How? Y
if
is
x
defined as max of x0.
varies from -2 to -3, then
If x is -2,
If
then
x
0 is
varies from
0 becomes
minus,
the greater than x, no? So max of x
yeah,
0 is 0.
now max if x ranges between
mhm.
-2 to -3, in that case it will y value will be
Then y will be equal to 0 only, no?
No, but why are you
Because
taking it as -3 to -2?
y equals
Again,
to max.
even if, okay,
Okay.
even if you take y is defined as maximum of x0, and you are
Okay, okay,
saying,
got it.
right?
Yeah,
You got
yeah.
it, no? Yeah. So this is for y less than 0. But what happens when y equal to 0?
It is zero only.
It is 0. Just check. So fy of y, you're saying you're finding fy of 0. So basically, you're trying to find probability that y is less than equal to 0. Okay. And y is defined as maximum of
Ma'am,
x comma 0.
sorry, but how fy of y equal to 0 when y is less than 0? Y is 0, I understand, when x is less than 0.
Because range of y is 0 to 1.
Hmm.
If range of y is 0 to 1, I mean, you're not
Yeah,
defining
okay.
y for less
Okay.
than 0, right?
Yeah. So, yeah,
So
good.
it should be 0. Okay. So now the maximum, if now I'm looking for the CDF at the point y equal to 0. So at this point, what happens is you are getting probability that maximum of x0 is less
Yes,
than
ma'am.
equal to 0, right? And if y is
Is
0,
0, ma'am.
so maximum of x0,
Ma'am, we have taken y
sorry,
to be 0, so max of x comma 0 is 0 itself, no?
ah, right. So it
Yeah.
is just 0, right? And when is this happening? This is you're getting y to be 0 when x lying between -3 to 0.
Hmm.
This happens when x lying between
3 to 0.
-3 to
0. Yeah.
0. Right?
Yes, ma'am.
And this is what? This is
3 by 4.
3 by 4.
Yes.
Yeah.
Yeah.
Now, if you look for the CDF when y lies between 0 to 1,
Hmm.
right? If y lie between 0 to 1, then in that case, what happens?
It is x. It is x. Y equal to x.
Y equal x, right?
Yes, ma'am.
Huh?
Hmm.
So
You can integrate that.
you'll have to integrate that and you will get y by 4 from here. But you are talking about CDF, right?
Hmm.
So you will also have to add the previous probability. So actually, this if you plot this function, that is maximum of x0, you can see that if
At 0, there will be a jump.
yes, so okay, no, not for okay. Wait. So at 0, you have a jump here. Wait. So let's not write this. So this is 3 by 4.
And then till from 0 to 1, there is a straight line from 3 by 4 to 1.
3 by 4, yeah. So for y lying between 0 to 1, you have something like this. And it goes like this.
Ma'am, again one confusion.
Uh,
Like, y is a continuous random variable, right?
no, we have not said that.
But its range is 0 to 1 and in a continuity.
We are just saying range is 0 to 1. If the range is 0 to 1, we cannot say that the random variable is continuous, because if you look over here, you got it to be a mixed kind of distribution.
0 to 1, like 0 to 1, when we are saying like in interval, we
Yeah,
are saying,
I mean,
right?
yeah, y lying between 0 to 1 is like, if this is 0, this is 1, y can take any value between 0 to 1. Even it is happening here, right?
But it is going
Y
to
is
take
taking,
every value, right, between 0 to 1, because x can take any value between 0 to 1. So it is continuous. It's not
no,
that
but
it can take, it is going to take.
you look at this CDF here, you see for if okay, what is the definition for a continuous random variable? The CDF should be continuous, right? But look over here, the CDF is not continuous for y.
That's what I was coming to actually. There's a jump in CDF, and
Yeah,
the,
so
the
it is
variable seems to be
since the
continuous.
CDF is not continuous, we cannot say that the y is a continuous random variable.
So if it is not continuous, then it should be discrete.
No, it is a
Mixture,
mixed type,
mixture.
mixed distribution.
No, distribution is a different thing. Now, distribution is like the probabilities we are talking about of the variable taking some values, right?
Huh. Hmm.
That
So
can be
here
mixed,
basically,
or that can be mixed or continuous.
at
That is a different thing.
0 there is a jump. So
It means that probability that y equal to
but
0 is
from the open interval 0 to the closed interval 1, this uh, this is a continuous function. But at 0 there is a jump. So it is not continuous, not discrete. So we call it a mixed type of distribution.
What you have just drawn is the CDF graph, right?
CDA for f by, yeah.
A PDF would be completely different.
PDF would be completely different, yeah.
We were here supposed to compute CDF or PDF in the
Uh,
question.
we were supposed to compute the PDF.
PDF.
So to find the PDF, we'll just have to
Differentiate.
differentiate. So if you
Ma'am,
differentiate, you get this.
can you explain that particular? Can you go a bit above? Yeah, the 3 by
Yeah.
4 plus probability of 0 less than or equal to x, that portion. Can you explain?
Okay. So we got all right. We looked for y less than 0. We look for what happens when y equal to 0. Okay.
Mm.
And now we have to look for what happens when y lies between 0 to 1. Okay. So using the CDF, it is f by of y is probability y less than equal to y, and is defined as maximum of x comma y less than equal to y. Okay. Okay. So maximum of x y less than equal to y. So when look over here, this the way y is defined,
Mm.
right? So whenever x lies between 0 to 1, this maximum is
X.
just x,
Mm.
right? So this happens when x lies between
0 and 1.
0 and 1.
Ma'am, like this, when we studied discrete random variables and continuous random variables,
Hmm.
the definition given was that if the range is continuous, range is a continuous set, then it's a continuous random variable, and if the range is discrete set, then it is a discrete. That, not about the probabilities taken, right? That was the definition given to us.
The range, the definition that was given is when the
It,
CDF is
it does not have
continuous.
anything to do with the probabilities of that. It is about range. Na? The variable itself is continuous or discrete. That is the point. So
No,
suppose given.
just by looking at this 0 1 interval,
Hmm.
um, we cannot say this variable is
Because that was the
continuous.
definition, ma'am. That was the basic definition given to us in like week
Okay, we
zero
can
has
say
given.
that the variable is continuous, but the distribution is mixed. That we can say. And
Yeah, that is
variable is,
different thing. But variable is discontinuous definitely.
yes, variable is continuous.
Right, ma'am?
That We can say, yeah, yeah, that can be said.
Now, for continuous random variables, we can define how can there be for continuous random variables? We talk now that the probability of taking a value is zero, right?
That probability of taking any particular value is zero. Yeah.
Now there's jump again in the. I don't know if I am
No,
missing it, but in the weak zero, sir, they clearly specified that discrete random variable implies that the range set is discrete, and continuous random
huh?
variable implies that then range set is continuous, right? Yeah, and here range set is continuous, so it is a
It is
continuous.
said continuous random variable implies, right?
Yeah,
Random variable implies range set is
continuous.
continuous. But here it is not given that it is a continuous random variable. It is given that range set is continuous. So P implies Q does not does not imply that Q implies P, right?
No, ma'am, that was the definition. No, it was
No, you
said.
just said continuous random variable implies range set is continuous. It is just one way.
No, okay, maybe I didn't say it like so precisely, but sir
Let's.
said
Is it the I couldn't recall what has been done in week zero, but I will check this. Okay.
yes, ma'am. Where the random variables were defined now before start talking about the different kinds of distributions, they defined discrete random variable, and this was the definition given. If the range set is discrete, then it is a discrete random variable, and if the range set is continuous, then it is a continuous random variable.
Okay, I will check that. Okay, if it has been done. We have a
Ma'am,
lot
are we
to go.
continuing today's session or?
Lot of it is left. Mean variance. Let's just finish this part. So as we saw in like in week three, you saw the
Just one small part in that finding the PDF, we would differentiate it, right?
yeah, we'll differentiate it.
Didn't we say that for
There also
y
is one.
equal to 0, it was 3 by 4? So we didn't use that so anywhere.
We used it, right? Yeah, we used it. So yeah, we have
This
used it
is
there.
this is CDF or PDF? This is CDF, right?
Oh yeah, right. It was correct. Maybe can change
This
it.
is
This
CDF,
is
and then
CDF.
we'll differentiate, right?
Yeah, you'll have to differentiate this to get the PDF.
So from the range of y from being 0 to 1, it would be 1 by 4, right?
It will be 1/4, right?
But then we just saw that the CDF of y was for y is equal to 0 was 3 by 4. Why aren't we using that?
Sorry, can you repeat?
Why aren't we saying the range
Mhm.
is specified as follows, that when y is less than 0, it's 0. When y is equal to 0, it's 3 by 4. And when y is between 0 and 1, mean y being
Because even if you put y equals 0 here, it is again, I mean, this equation captures both basically, right?
okay.
Put y
That's
equals 0, it will become 3/4. So it's basically 3/4 plus 5/4.
okay.
Yeah. Okay. So expected value is left. What else is left?
Ma'am, can we expect these kind of complex questions in our exams?
No, next distribution definitely is not happening.
Okay.
Will not ask for mixed distributions. There's a lot left there.
We continue
All
on
right.
like
So,
Sunday session.
uh, Okay, so what I would say is, see, the expectation part is not difficult. We can skip that, and in the Sunday session, we can. So okay, this week there is no Sunday session. It has been postponed to Monday, right?
Yeah.
Yeah. So we can start from this multiple discrete continuous random variable. I would suggest you to watch this expected value part on your own because it's quite easy. It just you are from discrete. You're just doing the continuous. In place of summation, you have got integration. There is nothing new we are doing here, so you can watch this part um on your own. It's quite easy. So in the Monday session we will start from this mixed the joint distribution where one is discrete and other is continuous from here.
Ma'am, session will on what time?
Sorry.
This session, Monday session will be on
it,
what time?
it is not there in the calendar.
No, ma'am, it is on Sunday.
It is on Sunday you're saying,
Yes, ma'am.
but it has been updated. Hmm?
I'm seeing yesterday actually.
It's not updated, ma'am. Still the
It's
open
not
session is on
updated.
Sunday.
Okay, okay. Thanks for reminding that.
It's showing Sunday 6 to 8 p.m.
Okay. That will change. Okay.
Monday at 6 to 8 p.m. ma'am?
Mm. Timing will send the announcement.
Okay, ma'am.
May I ask a question related to extra activity?
Extra activity. What is it now?
Since the extra activity is based on the data we collected in extra activity 2,
Hmm.
my data, what I understand, is a continuous variables, all of them.
Hmm.
So I don't know how they'll fit a discrete distribution.
Uh, you're saying the data you have got
Yes,
is
same here, ma'am.
So,
It
for
is continuous.
example, I have taken economic data for a number of countries, say 100 countries. So, for example, I've taken balance of payment or population and all this, their demographic and
okay.
economic data.
Okay.
So, obviously, that would be a continuous variable, if I'm not wrong.
I mean,
Like, for example, if you have population of
no,
different
no,
countries, that would be a continuous variable, na?
no, no, no. So again, you can go back to the very first lecture of week 4. I'm sure you will get the idea.
Sorry.
First lecture of week 4.
I mean, I don't understand. I mean, I feel my data is a continuous variable rather than a
No,
discrete
no,
variable.
just check that part. Just check the first lecture in week 4. You will
Oh,
get the idea.
okay. I don't
Yeah.
have to gather more data.
Just check that part. I'm sure you will get your answers.
All right, fine.
All right, then we'll close the session for today, and Monday session we will start from this discrete and continuous joint distribution. Okay.
Thank you,
Yeah.
ma'am.
Yeah.
Remember that.
Thanks. Thanks for joining the session.